Welcome students. In this lecture, we will talk about hypothesis testing. This is a very important topic, not only in statistical inference, but also in the subject of research and research methodologies. So let's start with it. Basically, by hypothesis, we mean the assumptions which can be tested, which can be verified under some analysis or after some experimentation. In statistics, this is, as I said earlier, it is a very important phenomena, and we will be seeing that what different types of hypotheses we have in statistics. Whatever the case is, the main purpose of statistics is actually to test the hypothesis. A research hypothesis which stands the test of time, that is, the hypothesis that has been tested and verified to be true, eventually becomes a new theory. In statistics, we have basically two different types of hypothesis. One is called the null hypothesis, symbolized with H naught, and the second one is called the experimental or the alternate hypothesis. The second one is called the experimental because it is tested or it is justified or verified after doing some experiment. It is called alternate because it is exactly opposite or alternate to the null hypothesis. And this is indicated by H1 or HA. That is, in the subscript, we can either use the alphabets or the numbers. We start with the null hypothesis first. Null hypothesis is a commonly accepted fact in a one sample case and shows no difference between the samples of groups in more than one group or more than one sample case, right? So basically, uh, a thing that is generally accepted, an opinion, a concept that is generally accepted in the population is basically what we call a null hypothesis, right? When we have taken one sample from the population. But if we have more than one sample case, then null hypothesis shows that there's actually no difference between the samples. There's actually no difference between the groups. Null hypothesis also shows the situations when dependent variable is not affected by the supposedly independent variable, right? So if we have an IDV that is an independent variable and a DV which is a dependent variable, then null hypothesis would show that actually that IDV is not the IDV for the DV that we are talking about, or the dependent variable is not changed by the independent variable that we are talking about. Rather, it would be changing by some other factor or by some other independent variable. For example, we can have some examples of the null hypothesis like that there is no change in water levels in spring, right? So we can see over here as well that if water level is the output or dependent variable and spring, that is the seasons, are the independent variables, then we are saying that the seasons, and particularly the season spring, is not changing the water levels. So this statement can be taken as a null hypothesis. For example, plant growth is not affected by light color. So again, the output or dependent variable is plant growth, and the independent variable is light color. And we are saying that this light color, which is an independent variable, is actually not the IDV for the dependent variable, which is the plant growth. So again, this statement can also be taken as a null hypothesis. Likewise, another example is age has no impact on musical ability. Again, age is an IDV or the independent variable, and musical ability is something which is the output or the dependent variable, and we are saying that there's no relationship between the two. So similarly, this statement can also be taken as a null hypothesis. Researchers work to nullify or reject or invalidate the null hypothesis. The job of the researchers are to invalidate the null hypothesis, and this they do by making an experimental or the alternate hypothesis. But we should remember that the null hypothesis is not called a null hypothesis because it is a null or a zero value. It is called a null hypothesis because it is nullified. It is being rejected. We try to reject it. We try to invalidate it. Examples of alternate hypothesis would be the exact opposite statements that we have for the null hypothesis. Like for example, if the null hypothesis was that there is no change in water levels in a spring, then the alternate hypothesis, which is exact opposite of the null hypothesis, would be that there was a change in the water level this spring, right? So the take-home thing is this: that researchers work to reject the work to reject, nullify, or disprove the null hypothesis, and researchers come up with the alternate hypothesis, one that they think better explains or in actuality explains the phenomena. Now, from where the story starts and what are the the intermediate portions of all this hypothesis testing, we can easily understand it by looking into a probability tree diagram, right? We can also discuss these things in the points that I have elaborated over here, but I personally feel that it's better that we discuss these points that I have written with the help of a probability tree diagram, and then we'll later on come to it. So in the beginning, we should have some research question, right? And in order to answer this research question, we start with a null hypothesis, but there's a certain probability that whether the null hypothesis could be true or it could be not true. So it's a purely probabilistic phenomena. In order to nullify this null hypothesis, we do the experiments, collect the data, and analyze them, right? And we, when we do these experiments and analyzing the data, we have already developed an alternate hypothesis against the null hypothesis. The output of our analysis could be that we find that the null hypothesis is true under the condition that it was actually true, and definitely it will be a true result, right? And it's an event, so it would have certain probability, and it would be given by this probability. So like probability of h naught is found to be true given that h naught is true, is also the probability of true result 1, and thumbs up for it. Definitely this should be the answer. That means that we have done the research analysis and conclusions in the proper correct way. But we can also end up in a situation that our results show this thing that the null hypothesis is not found to be true under the condition that h naught is actually true. So that means we have made some error, and this is called a false result 1, right? And definitely it has certain probability, which would be definitely 1 minus the probability of the true result 1. So its probability is shown as probability of h naught found to be true under the condition or given that h naught is true, or it is written as probability of false result 1. This probability or this event is also called as false positive, right? And its probability is also called as the probability of false positive or the false positive rate, and it is also called as the type 1 error. Now, why we call it false positive? Because when we are saying that h naught is not found to be true, then basically or indirectly we are saying that definitely our alternate hypothesis would found to be true, right? So we are saying that HA is positive or alternate hypothesis is positive, but this is an erroneous result. So that's why we call it as a false positive. It is erroneous because it has stemmed from the condition or it has branched from the condition that H naught was actually true. So that's why it is basically a false result, an error result, or a false positive result. We can also have a situation that when the H naught was not true, right? But we ended up into a situation that H naught was found to be true. That is, H naught is found to be true given that H naught is not true. This is an event and its probability would be given that by the probability of this event. And we can again see this thing that this is another error that can occur in our hypothesis testing. Okay. And this error is basically called as a false result 2. And the probability of it is called as the probability of false result 2. And we also call it as a false negative. And the probability of it is also called as the probability of false negative or false negative rate. Now, why we call it as a false negative? We call it as a false negative because if in actuality, if we are accepting H naught when in actuality it is not true, then basically we are rejecting our alternate hypothesis, or we are being unable to identify the effect which is actually present, and which in null hypothesis we are saying is not present, right? So HA is being rejected, or it is being said to be negative, when actuality it is not. So that is why it is called as a false negative. And again, a thumbs down for it because it is an error. Lastly, we can also end up in a situation, the fourth event that could occur, which is mutually exclusive of all the other threes that have been defined above, is H naught is found to be not true when in actuality H naught was not true. So again, we can see it's a true result and we call it as a true result 2. And the probability of it is called as the probability of H naught is found true given that H naught is not true, or probability of true result 2, right? So this is again a good result and a thumbs up for it. So we can see that these are all the hypothesis testing is all about the probability and all about the probabilistic situations, right? We tend to have the true result one probability higher as compared to the false result one. We tend to have, or we try to have the probability of true result two higher as compared to the probability of false result two. There are certain other nomenclatures that we use for these probabilities, like the probability of true result one is also called as probability of TP, it's a true positive, and the probability of true result 2 is also called as the probability of true negative, right? And it's a nomenclature that we use as PTN. Like for true positive, we use a nomenclature which is PTP, and its probability should be higher as compared to their their corresponding errors. So the probability of TP has an error which is the probability of false positive, and the probability of Tn has an error which is the probability of false negative, right? False positives are also called as type 1 error, and false negatives are also called as type 2 error. We use a symbol alpha for false positive, and we use a symbol beta for false negative. Now, whatever we have discussed over here, let's go back to the slides and see what we have written for it so that we can now understand these textual things as well. So as could be seen, hypothesis testing is purely a probabilistic process. In the research process, after defining the research question, we start the research methodology by first making a null hypothesis, or by first understanding the null hypothesis. There's a probability of either H naught being true or not true. H naught is our null hypothesis symbol. Remember this thing. We then make an opposite hypothesis to H naught, which is called the alternate or experimental hypothesis. We perform experiments, collect data, analyze the data to draw conclusions from it which makes sense. So conclusions must be sensible, logical. Our results could lead to either of the four mutually exclusive events or conclusions that we just discussed. These events or conclusions are also probabilistic, that is, each event has a probability of occurrence. These four mutually exclusive results are true result 1, and this is a true result and a true positive, and it shows the probability of truly accepting H naught when H naught is true. We can have a false result 1. This is an error and is called false positive or type 1 error, and it shows probability of falsely rejecting H naught when H naught was in actuality true. It also shows or it is similar to say it in this way, that probability of falsely taking HA to be true or positive when in actuality it is not. Since it's an error, so it's called a type 1 error as indicated just now, and we symbolize it with the symbol alpha. Please note this thing, that later on you will see that this alpha is the same alpha that we discussed in the confidence interval situation as well, when we are doing the estimation problems. Okay, false result 2. This is an error and called a false negative or type 2 error. It shows the probability of falsely accepting H naught when in actuality H naught is not true, or similar to say it in this way, that probability of falsely taking HA not true, or taking it as negative when it is present in the phenomena. So it's called a false negative, and you can also put it in this way, that it's a probability of being unable to detect the effect which is in actuality present. It is also called or symbolized with the symbol beta. True result 2. This is a true result and a true negative. It's a probability of truly rejecting H naught when H naught is not true. We want the probability of TP to be always higher than the probability of FP. FP is false positive and TP is true positive. Probability of true positive is also called as the sensitivity of the test. Sensitivity means that our test is capable to detect or identify even small effects or changes which are present in the phenomena. We want probability of Tn to be higher than probability of Fn. Likewise, just we discussed as for probability of Tp and probability of Fp. Probability of Tn is also called as the specificity of the test. And by specificity, we means that our test is very specific. Like from so many things, okay, from so many things, it is able to identify it. Or if from so many things the required thing is not present, then it would not say that it has identified it, but rather it would say that it is not present. So it's very specific test. It does not get overwhelmed in the presence of other variables, right? So I hope this is now understandable. The errors and the hypothesis testing phenomena that we just discussed in the probability tree diagram and we discussed over here, right? This whole thing can also be understood in a form of a confusion matrix. So if in reality H naught is true and we are rejecting H naught, then we are making an error which is type 1 error. And if in reality H naught is true and we are failing to reject it, then definitely it is a good result, a true result, and we call it as a true a true positive, as we just said, and it is shown by 1 minus alpha. Second case would be that if in reality H naught is false, then we are rejecting it, then definitely it is again a good result. And the symbols that we have used over here, I will just come now, just after discussing this second case of it, that if in reality H naught is false and we are failing to reject H naught, right? So if H naught is not present, but we are not rejecting it, so we have failed to reject H naught, then definitely we are making an error which we call the type 2 error in the statistics, or the false negative error, or the beta error. Now, please note this thing, that the sensitivity or the probability of being able to identify even smallest changes is 1 minus alpha, and the specificity, which is a true result, is also given by using the probability of type 2 error, which was beta, as 1 minus beta. And this 1 minus beta is also called as the power of the test, because our test is so powerful that it was able to identify the effect that was present. Okay, so that's how we indicate these power and the specificity and the sensitivity in terms of beta and alpha symbols. Now, researchers decide before doing a hypothesis test on a maximum probability value or a p-value for which they will reject the null hypothesis. So we can see this thing, that this whole process of hypothesis testing is either about rejecting the null hypothesis or accepting the null hypothesis. Now, whatever the case could be, if you are going to reject the null hypothesis or accept the null hypothesis, then researchers have to decide this thing before actually starting the process of hypothesis testing, that at which values or at which thresholds of probability they are going to do it. Okay, those values or those levels of probabilities at which they are going to reject the null hypothesis are basically called the significance levels, right? And that significance level is basically the probability that we also called as the alpha. So how the story goes is this, that if after the hypothesis testing we obtain a probability value which is actually less than alpha, okay, then we would say that our results are significant, our test is significant, and we have enough statistical evidence to reject the null hypothesis. But if what happens is that after hypothesis testing, our probability values or p values are greater than the significance levels or the alpha probability or the alpha value, then we would not be able to reject the null hypothesis. So these alpha values or alpha levels have to be defined before the hypothesis testing. Okay. So when a hypothesis test results in a p-value that is less than significance level, the result of the hypothesis test is called statistically significant and H naught can then be rejected. But there's a caution over here. Now the caution is this, that since we are using the samples to identify or get something or generalize the things on the population, the sample size matters a lot over here. What happens is this, that if we have a very, very large sample size, okay, then even a small difference or a small presence of the effect can be identified, detected very easily if the sample size is large. And why this happens? Because larger the sample size, smaller would be the sampling variations, or smaller would be the sampling errors, or better it would be representing the population. Okay, so the sample size matters a lot over here, and we have to be very careful that what sample size we have to take. This leads to some very complicated relations between alpha, beta, sample size, and the power of the test. And what are those complications? The complications are that higher the value of alpha that we take, lesser will be the beta value. Okay, but remember this thing, that the higher the alpha means higher the false positive rate, and we don't want to be a high value because we want it to be a low value. But the higher the value of alpha comes out to be, it leads to a very low value of beta, and we want beta to be a low value. So it's a matter of all the trade-off. Lesser value of beta, more will be the power of the test, and that's why we want the beta to be less, and easier it will be to detect a small difference or the presence of the effect. And the second case is that smaller the values of alpha that we actually want, higher will be the beta values that we do not want, and the higher value of beta would lead to small or lesser power of the test, and difficult it will be to detect a small difference or presence of the effect that we want to explore. So you can see that it's all the game of trade-off. Why, how alpha and beta affect each other, we will just look into this thing in the later slides to come. Now it's important for the researcher to decide first about the sample size, alpha, and power of the test. Usually what happens is this, that the sample size is taken greater than or equals to 30, and the usual values of alpha are less than or equals to 5% value, that is 0.05, and the usual power of the test that normally researchers are supposed to take should be greater than or equal to 80%. Probability of type 1 error is also called the alpha that we have just discussed. The significance level alpha is the probability, right? Now please note this thing. The significance level alpha is the probability of making the wrong decision when in actuality the null hypothesis is true. And that's what the type 1 error is about. So be careful with this thing. Type 1 error rate is the alpha, type 2 error rate is the beta. Now how these alpha and beta affect each other, we will explain it with a simple graph, and whatever we are discussing in the graph is all which is written in this slide. So we'll just discuss the graph and we'll understand what is written over here. Now over here we have two sampling distributions, as you can see. One is the sampling distribution given by the blue curve, and second is the sampling distribution given by the green curve. The blue curve sampling distribution is of the null hypothesis, and the green curve sampling distribution is of the alternate hypothesis, right? We must understand that these hypotheses, that is the null and the alternate hypothesis, are actually the sampling distributions. Okay, and definitely they follow a normal PDF, right? Because whatever we know about the population is from the sampling distributions, and in the hypothesis testing, we are actually trying to find something about the population. So this is all the game of the sampling distributions. So the concept that how the sampling distributions are formulated and their PDF is very, very important. And we discuss this thing in the lectures and the video lectures of sampling distributions and central limit theorem. Okay, now look into this red vertical bar over here. Okay, now on the right hand side of this bar and on the blue curve, whatever we have is the alpha or the type 1 error, right? This bar is basically at the alpha level, and the area of this thing, which is also shown by the diagonal hatches, is the alpha value, which is the type 1 error that we were talking about. And on the same red vertical bar, the left hand side of it, but in the graph given by the green curve or for the alternate hypothesis, these horizontal hatches or these horizontal bars basically show the these horizontal hatches, yes, basically show the beta or the type 2 error area, right? And we can see this thing that if we slide this vertical red bar on the right hand side, it will decrease alpha but increase beta. And if we slide this vertical bar on the left hand side, then it will increase alpha and decrease beta. So that is why we say that increasing alpha will decrease beta and vice versa. So let's do a little simulation to understand this phenomena, that how we are saying this thing that increasing alpha would decrease beta and vice versa. So let's do this little simulation. So I'm opening a blank empty slide over here, and let's make the layout to be completely blank, and let me bring these two normal distributions on the slide. So one is for let's remove this extra one. So one is for the null hypothesis and the other one is for the alternate hypothesis. Let me do some little changes over here. Let me first make this thing something bigger in size so that it is observable by everybody, because I'm not opening the slideshow over here, because I need to work on this slide so that we can understand it. And let's change the color of this one so that uh, it becomes different from the first one. So yes, the black would be different from the red, so observable. And also let's make it transparent so that we can basically slide it on the other one. Yes, this is much better. So okay, so let's make this one transparent. So this can be uh, moved quite easily. At this moment it is not transparent, so set transparent color. Is it working? No, it's not working. Let's do it again. Is this? No, it's not working. Let's try this thing again so that it becomes. Well, it should be working. Let me delete this one and get another one. Yes, and let's make this transparent. Yes, this is better now. So we get these hitches and glitches. Don't worry about it. And now let's change the color of it as well so that it becomes different from the first one. Yes, now there's a marked difference between the two. Okay, so let's assume this red one is the distribution or the normal distribution for the null hypothesis, and this black one is the normal distribution for the alternate hypothesis. Okay, and let's slide this a little bit over here. So this is the situation that we were talking about. Okay, and let's bring in the vertical bar, which is the significance level bar as well. So this is our vertical bar. Now please understand, try to understand what we are talking about. What we were saying was this, that on the right hand side of this vertical bar and on the red curve, we have the alpha. And let me increase the height of it. And on the left hand side of this vertical bar that we have just brought in, and on the left hand side of it, okay, so on the left hand side of this vertical bar, we have the beta, and this is on this second normal distribution graph, which is greenish black in color. Let's change the color of it. Okay, so that let's change the color of it so that it becomes more differentiable than the first one. Yes. So now this is much better. So what we are saying is this, that on the left hand side of this vertical bar and on the blue curve we have the beta. Now you can see this is the alpha and this is the beta. Alpha is on the red curve, beta is on the blue curve, alpha is on the right hand side of this vertical bar, and beta is on the left hand side of this vertical bar. Now if I start moving this vertical bar, right, let's say I moved it over here. Now what you can see, the area of alpha has increased and the area of beta has decreased, right? The area of beta is on the left hand side of this vertical bar and on the blue curve, and the area is on the right, the area of alpha is on the right hand side of this vertical bar and is on the red curve. So we can see that how these alpha and beta are related. Increasing alpha decreases beta, increasing alpha increases false negative, decreasing beta decreases false positive, increasing alpha decreases true positive, right, and decreasing beta increases true negative. So it's a big trade-off thing, a big confused trade-off thing, and this is the problem. This is where the problem starts. The researcher has to decide. The researcher has to give some emphasis, some dominance of one over the other, and this is the intelligence of the researcher, the data analyst, that how he does this thing, right? So I hope this is understandable now. We can also we can also understand this thing with another graph. Now again, this is on the left hand side we have null hypothesis distribution H0. On the right hand side we have alternative hypothesis distribution H1. And this blue shows the type 2 error or the beta, this red shows the type 1 error or the alpha, right? And these are this, again, the sampling distributions from their respective populations. That's why they are normally distributed. Okay. And in this other graph also we can see this thing, that we have on the left hand side the null hypothesis distribution, on the right hand side we have alternate hypothesis distribution, and this is the vertical hedge or the vertical line which is differentiating between alpha and beta, right? So this diagonal hedges are the beta on the left of this vertical line, and these diagonal hedges are the alpha on the right of this vertical line, and all the remaining thing on the right of this vertical line, on the sorry, yes, on the right of this vertical mark, and on this right hand graph we have the power of the test, that is 1 minus beta. So this is all the 1 minus beta thing, this is beta. This is all the 1 minus alpha thing, this is alpha in this upper graph. And over here as well we can see, if this is beta, then this is 1 minus beta. If this is alpha, then this is 1 minus alpha. 1 minus alpha will be on the blue curve, alpha will be on the blue curve, 1 minus beta will be on the green curve, and beta will be on the green curve in this graph, right? And over here as well, on the right hand side of this vertical bar on the blue curve, we have 1 minus beta. On the left of this vertical bar on the blue curve, we have beta. On the right of this vertical bar, On the red curve, we have alpha, and on the right of this, on the left of this vertical bar, and on the red curve, we have 1 minus alpha, right? So that's how these things go. These 1 minus alpha and alpha, these 1 minus beta and beta are the same things that we discussed in this probability tree diagram, right? This false result 1 was alpha, this true result 1 was 1 minus alpha, this false result 2 was beta, this true result 2 is 1 minus beta, right? So that's how these things are related to each other. Type 1 and type 2 errors are inversely related, as we just saw. As one increases, the other decreases. Type 1 or alpha error rate is usually set in advance by the researcher. The type 2 error rate for a given test is harder to know because it requires estimating the distribution of the alternate hypothesis, which usually is not known. So what we are saying is this, that usually researchers focus on the alpha value and the sample size and the power of the test. They don't focus on the beta values because for beta we need to have the distribution of the alternate of hypothesis, which we normally do not have. Let's take an example. Two drugs are to be computed. Sorry, I'm pardon me. Two drugs are to be compared in a clinical trial for use in treatment of a disease X. Drug A is cheaper than drug B. Efficacy is measured using a continuous variable y, where h naught such that mu1 is equals to mu2. So let's say that drug 1 belongs to population mu1 and drug 2 belongs to population mu2. We start with the null hypothesis that there's no difference between the two populations. There's no difference between mu1 and mu2. Now, what is type 1 error? Type 1 error occurs if the two drugs are truly equally effective. That is, in reality, there is no difference between the two, but we conclude that drug B is better. And the consequence of this error would be in financial loss, because then we would be making a lot of investment on making drug B, but in actuality there was no difference between the two, right? It's just like this thing that suppose we have a certain drug for a headache and another drug for the headache, and both are equally effective, but because of some errors we found this thing that this second drug is more effective than the first one, and supposedly the second drug was also more expensive than the first one. So this type of situation. Type 2 error occurs in this phenomena when if drug B is truly more effective, but we fail to reject the null hypothesis and concluded that there is no significant evidence that the two drugs vary in effectiveness. And what is the consequence? What is the consequence? The consequence can be rather quite destructive and even may leading to death as well, because we in actuality there was difference between the two drugs, but we did not take the second drug, understanding that both are equal. It's okay to take any drug, and ultimately it did not cure the ill health. Now, statistical tests. So far, we have seen that a hypothesis refers to a supposition H naught, which is to be accepted or rejected. Now, in statistics, there are two testing procedures for it. This hypothesis testing is done under the umbrella of two categories. Either we can have a parametric type of test or a non-parametric type of test. By parametric type of test, we mean that we make assumptions of the population distribution from which the sample is taken. And that basic assumption is that it follows the central limit theorem and it is normally distributed, right? And non-parametric type of test is this, that we cannot make any assumption about the population. So we don't know that what type of distribution it follows. And when we do the hypothesis testing in this situation, we call it as a non-parametric test. In the parametric test, there are two fundamental types of tests, which are z-test and t-test, but there are others as well, but the fundamental are two. A quick comparison of the two is this, that t-test refers to a type of parametric test that is applied to identify how the means of the two sets of data differ from another when variance is not given, right? Actually, the variance of the population is not given over here. And a z-test implies a hypothesis test which ascertains if the means of the two data sets are different from each other when the variance of the population is given. Based on the t-test is based on student t distribution and the z-test is based on normal distribution. The population variance is unknown, as just we indicated. in t-test and population variance is known in the z-test. The sample size is usually small in t-test. It is somewhat less than 30, 15, 25, 10, something like this. But in z-test, the sample size is quite big, quite larger. We will be focusing in our course on parametric test firstly, and then later on we will see about the non-parametric test. So the fundamental Z and T test can be categorized in parametric test as being one sample or two sample. If you have one sample from the population, it's called a one sample T test or one sample Z test. And if we have two samples from the population, it's called a two sample T test or a two sample Z test. In two samples, we have the case of samples being independent or paired, right? And when we have paired samples, we call pair t-test, and we have independent samples, we can have two groups of t-tests, and we can have a z-test over there as well. This is a table which shows different types of statistical tests that we have, like one sample, two sample analysis of variances, chi-square, f-test, Bartlett's test, Wilcoxon, Mann-Whitney, and Puskul-Wallace test, and there are many others as well, which we will see with the course of time, uh, that how they are worked upon, right? So thank you very much, students, for this lecture. If you have any queries, any problems, then you can write down in the comments, and I'll get back to you to answer your questions if you have any. So thank you very much.